Welcome everyone to the tutorial on audio fingerprinting. My name is Anup Singh. I am pursuing my PhD from Ghent University in Belgium, and I'm currently on a research visit here at IIT Kanpur. I closely work with Professor Vipul Arora, who is also my PhD co-supervisor. I mainly do research on audio retrieval systems. So my main focus is to investigate how to make these retrieval system more robust and efficient to make it scalable for its large-scale deployment. So in today's tutorial, I will be first giving an introduction on audio fingerprinting. And then in the next two parts, I will be discussing about the components that are required to build the audio fingerprinting system. And then at the end, I will also be discussing some existing methods on audio fingerprinting methods and as well as the indexing part. So let's begin the introduction. So have you ever been listening to a piece of music which would be a new track from an unknown band and wondered what it was? In the past, you may have had to ask someone in the hope that they knew. Uh, thanks to the but thanks to the modern technology, now what you can do is just record a piece of music and use one of several music identification apps such as Shazam, if you have heard of, or Google's now playing search engine, and it will tell you more information about that recorded piece of music. So the core technique behind or core technology behind these apps is called audio fingerprinting. Uh, so what is audio fingerprinting? So audio fingerprinting basically allows generating a compact summary of an audio signal, uh, because of which it allows in efficient storage of large database of audio files. And also, moreover, it also allows you to pass the pass retrieval of audio from that large pool of audios. So there are many applications of audio fingerprinting. First is music identification, as I just mentioned right now. And there are certain number of companies that have come up which delivers product based on this technique called audio fingerprinting. Another use case is monitoring the broadcast content. So it's useful in tracking the copyrighted content, and it's also useful in identifying the instances of unauthorized use or piracy of audio content. And the recent exciting application of audio fingerprinting has been in second screen apps, which basically provides users real-time information on their mobile devices, such as like mobiles itself or the tablets, about the broadcast content that they're watching on TV. So second screen apps basically allows users an interactive experience with the broadcast content. So audio fingerprinting kind of provides the complementary information to these second screen apps in terms of it lets the user or these screen apps to know what kind of content that is being broadcasted on this television program. So there are certain number of challenges that we need to tackle with in order to build a reliable audio fingerprinting system. So first is to ensure that the systems are to ensure that it's robust against various distortions such as noise and reverberation, for example. So just imagine a scenario like where you are in a gym and you heard a piece of music and you want to use your music identification app, but once you record a query, it's also possibly accompanied by a noise where people are chatting in the background, and maybe also could be a possibility of a reverberation. So you want that your this app should work well or should be able to accurately identify the music which is there in the audio query. So you want to ensure that the system are robust in that kind of environment setting. Second challenge is that the system should be fast enough to retrieve the required information to the user and ultimately enhance the user experience. So if you must have used Shazam or Google's now playing search engine, you record a piece of music and it gives you the information in no time. So you don't want that the information should be delivered in a delayed way. So you want that the experience should be enhanced for the user. And the third challenge is that the components that are required to build an audio fingerprinting system, they should be computationally inexpensive. I mean to say that so there are components that I'm going to discuss later in this tutorial. So for example, there is a fingerprinting component, there is also indexing component. So they should be computationally inexpensive so that so that they can be deployed on a large scale, maybe on a cloud server, and maybe they can also be integrated on the mobile devices, like which are uh, which have limited resources. So these are some challenges that we need to take into account while we develop this audio fingerprinting system. Um, so there are actually basically three components we need to develop to build the whole audio fingerprinting system. So there are three components. The first component is basically responsible for doing the processing of the audio. And then the second component comes in where you have a audio, which is the pre-processed one, and then how do you go from audio to the fingerprint? And the third one is responsible for search. So you collect all the fingerprints from all the audio files that you have in your database. You store them, you index them, and then in an offline fashion, and then you do online search, fast online search with the help of this indexing component. So in the coming slide, I'll be basically talking about these three components more in detail. And we will also be doing some hands-on session to see how these components are actually developed to build the whole audio retrieval system. Okay. So let's talk about the first component, which is for audio processing. So we have an incoming audio. So as you know, the waveform is a digitized version of the continuous signal. So the signal is basically quantized in both the, if you see in the GIF, it's quantized along the time axis, also along the y-axis, which is amplitude axis. So if you say that a sample, an audio is sampled at 16 kilohertz, that means you have sampled 16,000 samples per second. And if you say that it's coded into 16 bit, that means you have 2 to the power 16 possible quantized labels to which you have quantized these amplitudes. There's also a possibility of doing the pre-processing once you have this waveform. In pre-processing, you can do either resampling. So suppose if you have a very high sampling rate audio, then you can do it resampling like to 8 kilohertz or 16 kilohertz, depending on how are you going to implement this audio fingerprinting system. And then you can also do the audio normalization based on some RMS value or volume normalization. So there are some standard like LUFS based normalization that you can apply to it, to the audio waveform. And if you're also dealing with the speech audio, you can also do some sort of filtering. For example, if you have a speech audio, you can apply a pre-emphasis filter. Basically, get rid of the very low noise components using this filtering process. And then once you have this audio, you can transform this raw audio into the 2D representation. So what a 2D representation of an audio is. So there are many kinds of 2D representations. So one of the most popular representation is the spectrogram. And it's there are many variants of spectrogram depending on how do you represent the frequency component, the power of the frequency component. Okay, let me show. I should have on this diagram. So in this diagram, it's a diagram which shows the spectrogram. So along the y-axis, it gives an information about the frequency that is present in the audio. And along the x-axis, it represents the time. So it basically, this 2D representation is kind of telling you the evolution of the frequencies along the time axis. So this is one diagram which shows the spectrogram, and then there are many variants of it, depending on how do you represent the scale of this frequency. Actually, it could be on a log scale or like on a mel scale. If you see to date, whatever the fingerprinting approaches that have been developed, they don't directly process the original waveform, the raw waveform. So they first convert the raw waveform into 2D representation, like for example, spectrogram, and from there they generate the fingerprints. So this is what actually happens in the audio pre-processing. You do pre-processing, you convert the raw audio into the 2D representations. Once you have this 2D representation, then this is gets into the second component of the retrieval system, which is like fingerprinting. Then comes the next component, which is representation learning, or I would say, how do you go from an audio to the fingerprint, which fingerprint is basically just a normal low dimensional vector, which basically is kind of a feature which represents the audio. Based on the current literature, you can broadly classify the methods, the fingerprinting methods, like based on how do they generate the fingerprints. It could be rule-based or it could be the learning-based methods. So rule-based methods are the approaches where they, based on some heuristic or some knowledge base, they extract some features from the audio or one of the representation of the audio. So we call them as a handcrafted feature. We do not learn, but based on some heuristic, we are just extracting some features out of that audio. These features are actually quite robust, but they are not very robust when the distortions are at very high level. So most of the conventional approaches that have come up during like in 2000s, so they were mostly rule-based approaches to generate the fingerprint from the audio. Some of the most popular approaches based on this rule-based extraction of fingerprints are Shazam. And then there is also another method called Philips. I mean, just because the guys were from Philips industry. And there was another system called Fingerprint. It was developed by guys from Google who extracted the wavelets from the audio and then they binarized them into 0 ones with the help of min hashing technique. So basically, these are the approaches. What they do is you have an audio, and from audio you generate the features. And for the feature, we just refer to as fingerprints or embeddings. These are all things are analogous. And then there comes a second category, which is learning-based approaches. What they do, the recent approaches are actually leveraging these machine learning-based methods. So you have an audio, they directly capture the features from it. So they don't rely anymore on these knowledge-based or rule-based approaches. They just directly feed this audio to some machine learning model, and then machine learning model will give a feature out of it. And these features are actually have been proven to be more robust in high distortion environments. And if you see some recent approaches, these approaches basically use these machine learning models. It could be based on a RNN or it could be using CNNs, which are convolution neural networks. And recently, we also released one paper where we use transformers as a fingerprinter, which takes audio and gives the fingerprint. Transformers are actually known to have more contextual information that it embeds. So it makes the fingerprint more robust and discriminated. So in this tutorial, I'll mainly talk about, I'll discuss on how the fingerprints are generated using machine learning method. More specifically, how do we generate fingerprints using neural network model? So what are neural networks? So neural networks are basically nonlinear embedding functions, right? So if you want to develop a neural network based fingerprinter, you need to take care of these three things. If you see the diagram on the right, so the first thing is that what kind of an audio or input you are going to feed to the neural network model. So this is first thing. The second thing is what kind of a neural network architecture are you going to use? And the third thing comes in is that how are you going to train this neural network model? So whenever you have to design a neural network based fingerprinter, you have to take care of these three things. One is input, what kind of input you are going to take. The second is what kind of neural architecture you are going to use. The third one is how are you going to train this neural network architecture. So you must have come across like when you in the machine learning courses also, like when you train the neural network, it's based on the gradient descent optimization. So what are the possibilities of the input audio? What could be the possibilities of an input to the machine learning model? So it could be either a input waveform, a direct raw waveform, or it could be some intermediate representations like spectrogram or any of its variants, or it could be like a chroma-based input features, or it could also be like the embeddings from a pre-trained model that can be fed into this neural network model. And what could be the possible architectures for this neural network? It could be like CNN, RNN, or also it could be just a multi-layer perceptron network as well. So once you have trained this neural network model, you get the embeddings out of it corresponding to the input audio. And this embedding is actually called fingerprint. So you have audio, feed it to the neural network, a pre-trained neural network. So you train it, and then once you train it, you get the embedding out of it. And this is what we refer to it as a fingerprint. So I'll discuss about self-supervised learning. In machine learning, you must have come across self-supervised learning, unsupervised learning. But there's another learning framework called self-supervised learning. If you see the diagram on the left, you have a neural network and this one, and then you also have another two copies of the neural network. So it's just a replica of the same neural network. So I mean to say it just the three copies of the same neural network, and the parameters are shared across these three neural network models. So in this framework, you have three inputs. So one is xi, another is xj, and third one is xk. So we feed these inputs to the neural network model, and then model outputs the embeddings corresponding to these inputs. So first, corresponding to xi, you get fxi, and then fxj, and fxk. So these are the embeddings corresponding to the input xi, xj, and xk. And then you also compute the distances between these input-output embeddings. So what is the purpose of this self-supervised learning is that you want to preserve the similarity in the input space and in the latent space. So suppose you have an input which are related in some aspect in the input space, you feed it to the neural network model, you get the embedding, and you want that embedding which corresponds to the related pair of input sample. They should also be close together in the latent space. For example, like in self-supervised learning framework, you have a tuple of three samples. So xi and xj, they are relevant in some aspect, and there is xk sample which is not related anyhow to xi and xj. So we have this terminology in the self-supervised learning framework. So xi is called anchor sample, and you have its counterpart xj, which is related to somehow xi in some aspect, and this is called positive sample. And then you have this xk, which is in red color, which is not at all related to xi and xj in any aspect. So we call this as negative sample. So in this diagram, if you see what you want to do with the help of this self-supervised learning framework is that you want that xi and xj which were relevant to each other, the embeddings that comes out of this, they should be, I should have written fxi and fxj, sorry. So my fxi and fxj should be close to each other in the latent embedding space, whereas my fxk should be far apart from these two other samples, fxi and fxj. So in a way, we want to just preserve the similarity. Do I make sense? So in the previous slide, I just talked about like in previous slides. So we need to take care of three things. So we need an input, we need a neural network model, and third thing is how we are going to train this neural network model. So for our tutorial on audio fingerprinting, so we are going to take the log MEL spectrogram as an input. The second thing was the architecture. So we are going to take the CNN architecture. Third one was how we are going to train the neural network model. So we are going to use self-supervised learning framework. So in our context, as I said, xi, xj are relevant to each other in some way, and xk is not relevant. So for our purpose, xi is just a random audio segment that you have taken out of some audio file, say of 1 second. And xj is a distorted version of it. So we add some noise, something else to it. So they are relevant to each other, right? In terms of the acoustic content that is there in both xi and xj. So they are related to each other. And xk is some random audio segment that we have taken from some other audio file. So this is how we construct these three things, xi and xj and xk for our purpose. And then we also have this contrastive loss, so which is actually capturing this phenomena, this one, which makes sure that the embeddings that are relevant, they are close together, and that the ones which are not relevant, they are far apart in the latent embedding space. And then how do we generate these distorted sample XJ? We randomly add noise signal to it, or the reverberation, or also the time offset, or it could be a combination of all those three. It just stochastically, we just add these kind of possible augmentations to Xi to create XJ. Why do we consider only these three kind of augmentation? Because this is what we are expecting or assuming that these are the possible distortions that we can come across in the query. So what we want, what is the ultimate goal of having this kind of Xi, Xj, and Xk is that we want the fingerprints should be very similar, corresponding to the clean audio, which is Xi, and the embedding that comes out of Xj, which is distorted version. The embedding that they comes out of Xi and Xj should be very similar. So this will make sure that the fingerprints that you are getting in this way are robust. So actually, we are addressing the robustness aspect of the audio fingerprinting system through this learning framework. For noises, we consider adding the noise in the range of 0 to 25 dB. And then we also, in the case of reverberation, we take room impulse responses. So which has a T60 label in the range of 0.1 to 0.8. So the higher the value it is, the higher the reverberation is there, that higher RIR. So more by reverberant that acoustic will get correspond to. We are going to do a little bit of coding. You must have received an email, right? Can you all open the Google Collab session? What's that? So first we are going to clone this GitHub repo where we have all the codes for audio fingerprinting. You click on the file section, there will be a folder now in the name or search. And then we are going to install some dependencies also to run this code. We also need to mount this Google Drive because in the mail you were asked to keep this one folder in your Google Drive because that will be needed now. And some input practice. Okay, so first we are going to look how the waveform look like. So if you have cloned this repository, it already contains some audio files. So we are just randomly going to read one of those audio files and just plot them. Just plot one audio file. So you can see this one so audio file which is normalized between -1 to 1, and I'm just plotting just 2 seconds of random chunk from that audio file. If I plot the whole audio, it will not look good in the plot. Okay. This one. Okay, we loaded one audio. I just showed the plot of some small chunk of that audio. Play that audio as well. Uh, and then I was discussing about this 2D representation in the first component of the audio system. So we can compute the spectrogram from raw audio, and so this is the audio that we loaded. We are going to compute its log mel spectrogram as well as just the spectrogram. So if you see, there are some parameters that are required to compute the spectrogram, right? We compute the DFT, so you need the sampling rate, the length of the FFT. So these are some of the parameters that are required to compute the spectrogram. Okay, so for that corresponding audio, we have got this 2D representation. So first is the log mel spectrogram, where we are taking the mel filter banks, and then other is the log spectrogram, where the frequency intensity is represented in terms of log. But for our purpose, we are just going to use this log mel spectrogram, which was the first requirement as an input to the neural network model. So we already have a pre-trained neural network model, or you can say pre-trained fingerprint generator. Link for that Google Drive. Oh, so did you already downloaded the? No. Okay, because there's another thing that is required while executing this whole tutorial notebook, apart from this notebook. There is also a model checkpoint that you need to load it in your model. So there are two things that no you yes. So if when I'm executing this thing, okay, this line, you see, that's why I asked everyone to put this thing on your Google Drive, because we are directly reading that audio, this checkpoint directly from your Google Drive. This one. If you have already mounted your Google Drive, okay, let me show how did I get this path. I have mounted this drive. I have this WiSSAP folder. You must have also somewhere stored in the Google Drive. So I'm just going to take this path and copy it. So this is the same path. This is the same path that I have. So what I'm doing right now, I already have a pre-trained model. So you need some model checkpoint. So I'm just loading back to this model, and then I'm just using this as a pre-trained model or a neural network based fingerprinter. I can send you the link. Not aware of it. Somebody from the technical team must have sent you the link. I can wait until you set up the. Here it is. So you guys have to change this path depending on where you have stored your CKPT file. Just have to run this cell and then I'll go back to my talk. So maybe you can, in the meanwhile, you can set up the. Okay, so we have seen how to load the audio. Does it look like in a time domain? And then we converted its 2D representation. We showed just the log mass spectrogram. One of its variant and the other variant is log spectrogram. And then in this cell, what we are doing is we have already trained a neural network model, load its weight, and then we are going to pass an audio to it, and then we get a fingerprints corresponding to that audio file. Okay, so it generates the fingerprint. So if you see in the output, what it is doing, it's randomly taking one audio file, which is named 00170.mp3. And then it is computing these fingerprints 291 number of fingerprints from this particular audio file. And the embedding dimension is 128. So it's a it's a NumPy array, which is 291 cross 128. So why are we getting this 291 instead of just one? Because we have an audio file, we are doing chunking with an overlap window. So for every overlap window, we are computing one embedding. So it's a 30-second audio, and for every 1 second, we are computing this one fingerprint with a hop of 100 milliseconds. We are getting 291 number of sub fingerprints from one audio file. So I just wanted to show you how we are getting these fingerprints for an audio file. So now comes the last part of the audio fingerprinting system, which is like last component. So what we do is, what is the search task now? So you have an audio query and you want to find the most similar audio from your reference data files. So what we do is, now we have a pre-trained model at hand. We have a audio query, you compute its fingerprint. So you have one embedding or one representation of that query audio. And you also have a lot of audio files which are in your database. So using that pre-trained model, you compute its fingerprints and you have stored it in some way. So you do this process of computing fingerprints from all your reference data files offline. So what is the task of search now is that you have a one fingerprint that corresponds to the query and you want to retrieve the most similar fingerprint and then you need to retrieve the most similar fingerprint and its corresponding that audio file. So you pass this audio query fingerprint and then the fingerprints of all the database to this matching algorithm. It will do the matching and it will give you the most similar fingerprints, most similar fingerprint and its corresponding audio. But this is a problem actually. We can't do linear search or a brute force search. Like suppose you have a query and you keep doing similarity with all the fingerprints, because in practice we have billions of songs, and when you generate the fingerprint, it could be like even more than 10 billion or maybe in a scale of billion. So you're not going to compare one fingerprint with all those billions of fingerprints. It will take a lot of time. So we need to rely on some fast search algorithms. So this is the second aspect of what I discussed before, the second challenge of building the audio retrieval system, that the system should be fast enough to retrieve the information from and deliver it to the user end. We cannot rely on brute force search. We need to have some fast indexing algorithm or the search algorithm to efficiently find the most similar fingerprint from your database. What are fingerprints? So fingerprints are embeddings, and embeddings are just the vectors. So you have a pool of billions of vectors, and you have a query which is also a vector, and you just have to find the most similar vector from that big pool of vectors. You can't do brute force search, as I said, and you need to depend on some fast searching algorithm. So there's another domain of this. We call this approximate nearest neighbor search algorithms. These are actually around 1,000 times faster than this linear search or brute force search method. Why do we call approximate nearest neighbor search? Because it provides you the nearest match, but with some probability, with some high probability. It will not make sure that every time with 100% probability you will get the nearest match, but with some trade-off, you can make sure that with a high probability you will always get the nearest match of that particular vector from that pool of vectors. So to date, there have been itself a research domain, like how can you design such algorithm where you can find the nearest neighbor search efficiently without comparing with all those n number of items. So there are many algorithms. One is called locality sensitive hashing, which is based on hash based algorithm, which is the hash based algorithm. And there's another called product quantization, which is basically based on vector quantization. It quantizes these vectors which are in your database, and based on that, it does fast search. And then there's another popular method for searching is called hierarchical navigable small world, or HNSW, based on a graph structure. So you create the graph, and based on that, in that graph, it traverses and finds the nearest match. So what I want to convey is that we can't do brute force search. We need to rely on some approximate nearest neighbor search to find the nearest vector. Okay, so what goes on in this indexing component? This is what I want to show through this diagram. So you have a lot of audio files in your reference database. So for every audio, what you do is you generate the fingerprints. As I said before, you generate the fingerprints offline. Suppose you have an audio, you do the chunking. So you create a chunk of 1 second with some overlap, like what we do in spectrogram, or like you have a sliding window, somehow it slides and particular length is there. So what you do is you chunk this audio with some overlap. Suppose you have 30-second audio with an overlap of 100 milliseconds, you will get 290 chunks. And we just saw in the example, in the code example. Now for every chunk, what you do is we pre-process. Okay, this was the first module that it does pre-processing of this whole audio, and then it chunks or it do segmentation. And then what happens? You have some number of chunks. You compute the log-mel spectrogram of it. Suppose you have 30 chunks, you will have 30 mel spectrograms. right? So you have one chunk of 1 second audio, you will compute its 2D representation, right? So you have this one audio, you pre-process it, you have 30 chunks, say. So for every chunk of audio, you compute its log. Can you repeat? Why are we? If you see this, this one, we need to take care of three things. First, what kind of input audio are we going to feed into our neural network? So neural network model expects some form of an input. Second is what kind of architecture are we using right now? Third one is how are we going to train that model, right? So in this example, if you see what we are doing, instead of raw audio, we are computing this log MEL spectrogram of that audio. Now this becomes an input to the CNN architecture. So CNN expects image like input. So this is what we are doing. We chunk, we compute its spectrogram, it becomes like an image, and then it goes into the pre-trained neural network. Neural network is just the order fingerprint. Does that make sense? And then we repeat this for all the audio files that we have in our reference database. So this was a process that I showed for just one file. And also in the coding that you saw that for one audio file, you had like 291 number of embeddings and each one was of 128 dimension. Okay, in the coding session, what you will see is that we'll implement this step of indexing. So what happens is once you collect all the fingerprints from all the audio files, it will generate three pickle files. When you will see in the coding session what each file represents. That's what I want to show. So there will be one pickle file with the name files. It will just contain the name of all the audio files that are in your reference database. Song1.mp like that. And then another pickle file will be created with the name of emd_dp, which basically is a big array of all the fingerprints that you have extracted from all the audio. So if you see in orange, this means that you have extracted 6 fingerprints from first audio file. And then you have extracted more like 5 fingerprints from the second audio file. And then you have just stacked to each other. Yeah, so it's just like you take one audio file, extract fingerprints, put somewhere, and another audio file comes in, you just stack another. So you keep stacking these fingerprints that you have extracted from all the audio files. So now it becomes one big array where you have all the fingerprints. So what is the dimension? The dimension of this array is n cross d. So what is n? Number of chunks, or you can say number of fingerprints, and d is numerical, right? Because we are getting a neural network, feeding to neural network, you're getting embedding. So that embedding dimension also has is there. So d is the dimension of that embedding. And then there is another third file which is named metadata.pkl. So what it has is the associated metadata for each fingerprint. So the first thing that you see in this, the first element, it means that the first fingerprint comes from the index, from the file index 1, and it corresponds to the chunk that is extracted from 0.0. So it is the starting time of that chunk. And then if you see this second one, it means that this segment, the second fingerprint. So this is the metadata associated to the second fingerprint. So this comes from the first audio file, and it corresponds to that chunk which started from 0.1. So what is the length of this array? And so the length of this array would be n, right? because it just contains the information about each fingerprint. Okay, you have extracted fingerprint, but you don't know what is from which file or from which timestamp does it come from. So you need to store that information. So you have n fingerprints. You need to keep information for each fingerprint. Yeah. Yes. Yes. So these are the three files that will be created when we when we will implement this indexing step. Now what happens is, now since you have this big array of fingerprints that gets feeded into this approximate nearest neighbor algorithm, which is indexing algorithm. It indexes this big chunk of array, and how does it look like? It's kind of if we use locality sensitive hashing, it's like as I just mentioned before, there are different indexing algorithm. One is hash based indexing algorithm. So it uses this big array and stores it in a nice way in a hash table in some sort. So I will discuss about hashing as well in the later part of the tutorial. So these are the 4 files that will be created once we implement this indexing step. In research, mainly we use this free music archive, which is around $8,000 of data, and it has multiple subset out of that data, small, medium, large, and full. So full corresponds to $8,000 of audio data. For our tutorial purpose, I'm just going to take a tiny subset of this data, which just has 114 files, if you must have seen in your folder. And how do we evaluate the fingerprinting methods? So there are basically 2 tasks. First task is that given a query, you need to identify from which audio file does it come from. So this means core search. You just broadly need to know which is the audio file that this query is coming from. But the second task is more refined, where you also precisely want to know that, okay, this is the identified file that we have for that query, but we also want to know which part of that audio file it is coming from, that audio, from that very audio. So there are basically 2 tasks, or you can say core search and fine grained search. We do use some heuristic approach to detect to precisely locate the timestamp within that audio file. And then there are 2 metrics based on which we evaluate the performance of the fingerprinting methods. First is the recall rate. If you see this example, recall rate tells us that how often your desired result has been found within that top rank. So let's say we have 4 queries and we have retrieved the best matching items, and they are sorted in based on the similarity. So you have query 1, query 2, query 3, query 4, and for query 1 you have retrieved some items using that audio approximate nearest neighbor search algorithm, and then you have sorted these items based on how similar are those items with respect to the query fingerprint. So these are some blocks which are green colored and with R. So that means these are the desired results that you want to have. So recall rate, as I said, it means how often have you found your desired result or relevant result in top K rank. So suppose if you want to find the recall at top 1, and if you consider this example, so the recall rate would be 3/4, because you have found out of 3, you have found the relevant ones in 3 cases out of 4. Likewise, if you consider recall at top K, you will consider how often your relevant result has been found within that top K rank. So if I say recall at top 5, it will be 1. Because even though it is not at first rank, but at least it has been found within top 5 rank. So this will also be considered as a valid match. And then there is a mean reciprocal rank that it tells like how, on an average, your desired result, on which rank did you find your relevant result. In this case, in the first example, you have 1/1 and then 1/1 again. And in this third case, your relevant result was found on the rank 5. So this term would be 1/5. higher the MRR, the better it is. It means you have found your relevant result at the top rank, one of the top ranks. Okay. So we'll basically see the indexing step that I discussed before. Okay, so up till now, I just showed that we have a pre-trained model, give an audio to it, you will get the fingerprint. Now, I also discussed in the third component, the indexing component. So how are we going to build the fingerprint database for all the audio files that we have? Um, so the material that I gave you, it has 114 audio files only. So with this step, what it will do is with the help of fingerprint generator, it will generate all the fingerprints for all the audio files. So it's generating fingerprints for all the audio files. So if you see in the cell, the first line corresponds, you need to mention what are the files name that you want to keep. And where do you want to save those files? After this step, there must be a folder created in hot search with the name fpdatabase. And if you go in that FP database folder, these were the three files that I was mentioning about in my previous slide. EMDB files metadata. Okay. And then I also mentioned that once we have this big array of NumPy array, of big array of these fingerprints, we are going to feed it into one of the indexing algorithms. So this is the cell that what it does. So what we also do is the embeddings that we get out of fingerprint or that neural network model, these are not normalized. So we first length normalize it and then we pass it to the indexing algorithm. So up till now, there are only three files, but with the execution of this step, there will be another file created with the name of fp.index. Right? Okay, since now we have indexed the audio file, now we can perform the audio search. For audio search, we need some. So we are also going to show with the queries that are clean, just the clean, or it could be also what I said, like it could be possibly distorted with some noise, reverberation, or with some time offset. So we want to do some. Just wanted to show some examples where we are doing the search with this indexing, with this index that we have created right now. So this cell will just instantiate our search module, and it will also load some noise audio file that will be required as well as the RIRs. Okay. So now we are going to randomly take one query, which will be of length 3 seconds, which is just randomly taken from some audio file with some offset. course it will be there. And then we are also adding some noise to it. So this one is giving me a noise added query where there's only noise in the query. Where the noise is added to the clean query. Clean is just nothing. We have just taken random chunk out of that audio file. This is the one where we have added noise as well as the reverberation randomly. And then we also have another kind of query where we have just added reverberation to it. It's a clean query that we have just expected. This is the query where we have added noise. So if you see, if you hear, there is a police siren in the background. This is the one where we have added reverberation to it. And the last one is where we have added both. So we have 4 types of queries which represent the same content, and we are interested to find from which body file does it comes from, even though we are distorted with this added background things. So we are going to execute this step, and it will tell, it will perform search actually. Okay. So this is the ground truth. So we extracted this query from this audio file with the name 001 nametime1.mp3, and this was extracted from this starting from this 22.91 second. Now we are interested to know, does our search module can find the query within that reference audio files or not. So in the case of when we have clean audio query, it is very precisely able to, it is able to okay, so in the clean query, in the case of clean query, it is able to tell that, okay, this was the file that they have found, and this was the time retrieve timestamp. Likewise, in the other types of queries as well, when we have added noise reverb added, you can find that it is able to correctly identify the audio file name as well as the timestamp. Yeah, we can add, actually for the tutorial purpose, I have just removed it, but we can, yeah, if you use this code from a GitHub repo, it will give this evidence as well. Yeah, I'll just run one more experiment. The noise is too much. It's like I've added a noise at 5 dB SNR. Let's see what are the results. Okay, so in all the cases, it is able to identify the audio file, and it is precisely able to find the timestamp as well. But it is able to find it just because we have very small amount of data files in our reference database. But it could be also possible when you have a lot of fingerprint in the case in scale of million. There will be cases where you won't be able to find this audio file. But for tutorial purposes, and it was not possible to show you the example with a very large database. Okay, this was it. So there were 3 things that I wanted to discuss with you. One was the audio processing. The second was how do we generate the fingerprints. The third component is once you have this trained model, you generate the fingerprints of all the audio files, you index them, and you do the search. Yeah, I'm just briefly going to discuss the existing methods on audio fingerprinting and indexing. Uh, so I mentioned Shazam also in one of the categories, like when I was discussing about rule-based approaches for audio fingerprinting. Shazam was probably released in around 2002 or something. Uh, how does it learn the fingerprints? Or not learn, but it generates the fingerprint based on some heuristic. So what is the heuristic? So they have this uh, well spec just the like the spectrogram of an audio. They generate the fingerprint. They generate the spectrogram of an audio, and then they capture these peaks. The peaks corresponds to the strong frequency component that are there in the spectrogram. Why do they choose these peaks as the feature for creating the fingerprint? Is because these peaks tend to remain even when you add the noise. So that is that this frequency peaks becomes like a robust feature. So Shazam used this heuristic or this noise-based approach that okay, these are the peaks that will still remain when you add the noise. Why not take these peaks as the noise robust features? Um, and based on that, they create the fingerprints. Uh, to also add some more robustness to these structured fingerprints, what they do is they first generate these peaks, and for a particular peak, they define a target zone. So within that target zone, there will again be a lot of peaks which will fall in that target zone, and then they create the pairs, anchor, and the peaks that the hash table. So there will be a lot of pairs of anchor and the target anchor and the starting point of anchor, and then they build a hash table. Yes, yes. No, no. What we are doing right now, what we are doing is suppose you have 1,000 files. How are you going to represent that those audio files? These peaks? Yes, yes. So they select one peak and then they define some particular region around that peak. So it could be, yeah, as you said, like you have extracted, if you consider that one peak which is located at 1.2 seconds, and then they will define one region like plus minus zero point 0.1 second, let's say. And then once you get these keys, they form the pair and then they build a hash table. And then with some heuristic, they did find that which audio file it is coming from. Yeah. So this was about the ZAM approach. And then we come up to the learning approaches, the second category. So in one of our, so this was our work where we wanted to kind of do something very similar to Shazam. So we have CNNs. So we get features from each CNN block. So we wanted to have this. We wanted to implement this idea. Can't we also do some find this interesting patches within that CNN architecture, like what Saddam is doing, like finding these peaks which are salient. So we also wanted to have something like that to detect the salient patches within those CNN features. And how do we do it? We do it with the help of spectral temporal attention mechanism that we propose. So it kind of enhances the CNN features which are there in the CNN blocks. Um, and then we also use this. What kind of architecture we use? It was ResNet-like architecture. We have residual connections, but it was just that we also kind of enhance those CNN features with the help of spectral temporal attention mechanism. And then there is another fingerprinting method from Google. So Google also, as I said, there are three components, right? Input audio, neural network architecture, training. Uh, so what Google does is they have input audio. So input type is spectrogram. Uh, what is the neural network architecture? They use CNN architecture with the help, and they also use spatially separable convolution layers. Spatially separable convolution layers are nothing. They just in the CNN you use two-dimensional kernels, but in spatially separable convolution you just decompose them into two one-dimensional kernels. So this is mainly used to reduce the number of computation to reach the same value. So the value that you get using that 2D convolution kernel, you will get the same value if you decompose those two-dimensional kernels to two one-dimensional kernels. If you see the mathematics, it will just reduce the number of computations. That's the main idea behind using spatially separable convolutions, as far as I know. And how do they train? They use the triplet loss function, which is very similar to what I just mentioned before in self-supervised learning framework. So the last thing, what is LSH? So I discussed about this indexing algorithm. So how do they search very efficiently? So this is one of the indexing algorithm which is based on hashing. So the core idea of LSH is that so map the similar samples to the same hash code. How do we generate? How does LSH generate this k-bit hash code? Is that they take randomly k number of random hyperplanes in a d-dimensional space, and for a particular sample they project like does it belongs to the upper side of that hyperplane or does it belong to the downside of the hyperplane, and depending on that they assign bit 1 0. Yes. So if you see in this diagram, so there are three randomly chosen hyperplanes. And say suppose for this point which is diamond, we want to assign one 3-bit code. So we see that it's above this hyperplane, so we have assigned 1. And then this is below with respect to this hyperplane, so we have assigned 0 for the second bit. And the same point is above with respect to the blue hyperplane, so we assign 1. So depending on what side of this hyperplane they are located, we assign 1 0 bit. So that's how we do binarization of these samples. So in our context, what are these points? These points are just the vectors or fingerprints that we have, right? So we have fingerprints. We are assigning these binary values to it, or we are assigning some hash code to each fingerprint. Okay, this was what I was discussing before. So now what I said is they have randomly drawn these k hyperplanes independently. So the possibility could be that the nearest point could possibly could be mapped to some different hash code. So it could be possible that with for this point, this was the nearest neighbor, but it has gone to some other bucket, or it has been assigned different hash code. So it was 101, but maybe it could be possible this was assigned 110. Okay, I should have said something before as well. So, okay, how does LSH search so efficiently? So, for all the points you assign this binary coding. Now, when the query comes in, you again do the same process for that query point also. Now you see, okay, to this hash code it has been mapped to. Now you retrieve all the points which were mapped to the same hash code. So suppose you have a query which was mapped to 101, and then there were other samples in the reference samples that were also mapped to 101. You retrieve all those samples, and you will just do the exact distance computation with of query with only those points. So in a way, you are reducing the search space. You are not comparing with the points which are here in this bucket or in the other buckets. You are just comparing only the points that were mapped to the same hash code. That is how you are reducing the search space with the help of locality sensitive hash. But the problem here is that since the hyperplanes are drawn randomly, there could be possible that the nearest point that you were looking for, it has been mapped to some different hash code. Yes. So there are also learning-based approaches where, so this is unsupervised way because you're just randomly taking independently these three hyperplanes, but there's another domain of this research, like how do we learn these hyperplanes with the help of machine learning? Yeah. Yes. Yeah. Yeah. So I'm just discussing the very naive, uh, the first version of LSH here right now. Um, so what I said is it could be possible that the nearest point has been mapped to the similar hash to a different hash code, and you will never see that point to do the exact distance computation. So how do we overcome this problem? Is that LSH proposes that you do the same process L times. So for one set of uh, hyperplanes, you build a hash table, you retrieve those points, and you do the same process L times. So you will have L hash table. Does that make sense? We may not even need we may not even need multiple hash tables. We can use hyperplanes in a clever way. So I'm going to mention about something later. Uh, so what I said is like you do repetitively L times, you will have L hash table. You have a query. Now you have k set of hyperplanes, and then you retrieve the points from all across the L hash tables, and then you do the exact computation. So there's a nice mathematical proof for it. Why do we need to do this repetition L times? The more you repeat this process, there's a high probability of finding the nearest match. Um, yeah, so this was about LSH. So if you're interested, you can read also other like recent approaches on fingerprinting methods. There was this one paper that we published this year. So you must have understood like now that there were two components, fingerprinting and indexing. So these were kind of independent to each other, right? So you generate the fingerprints. This was one step. The other step was indexing, where, for example, in LSH, what you do, you have points and then you assign them 10 bits, right? So these are kind of independent to each other. So in this work, what we did is uh, we kind of learn the fingerprints as well as the binary representations in an end-to-end way. Another problem that we came across in LSH was that the points that are there in these buckets, they are not uniformly filled. If they're uniformly filled, then this algorithm is very fast. It has a complexity of log n, but it doesn't achieve that complexity just because the buckets are not uniformly filled. But in our recent paper, we did two things. We wanted to learn this fingerprints and the bit representation in an end-to-end way. The second thing, we made use of optimal transport to make sure that the points are uniformly filled across these hash buckets. So as you said, may not need to have more hash tables. So we just had only one hash table with the help of this approach. So in the coding session, we also made use of this Fires.ai. It's a package which basically provides all sort of indexing algorithms that you may use. Yes. For more queries, you may contact me via email, or you can also contact me on Twitter. Thank you.